past how we can take something like 9 to the x, and if it's more convenient for us to write this as a power of 3, we could call this 3 to the 2x, because 3 squared is 9, and so we'd have 3 to the 2 to the x, multiply your exponents, and you get 3 to the 2x. And in the same way, if we wanted to do 2 to the t power, and it was more convenient, for whatever reason, for us to write this as a power of 8, we could say this is 8 to the 1/3 t, or t over 3, because the third root of 8 is 2, and we still have the exponent of t. We've done this before in the past. And this works fine if there is some common base between the two numbers. 9 and 3 are both powers of 3, 2 and 8 are both powers of 2. If we did something like 9 and 27, 9 to the t, and we want to know 27 to the what, well, then we would do something along the lines of this, where we would say that 9 is a 3 to the 2t, and that 27 is a 3 to the third, and then we've got this empty space there. And so now that we've got the same base, we can say 2t equals 3 times something divided by 3, and we see that this has to be 2/3 t. And so 9 to the t is the same as 27 to the 2/3 t. And as long as there's a common base between the two numbers, this always works fine. But there's no reason why we shouldn't be able to do the same thing, even if there's not a common base. 2 to the t equals 10 to the something. Not a common base between these, but every time, if we're starting with a base to just the x or the t or whatever power, when we changed the base, we ended up just multiplying by some number. Here I multiplied by 2. Here I multiplied by a 1/3. Here I multiplied by a 2/3. There ought to be some number that we could multiply t by, so that 2 to the t equals 10 to the some number times t. And our goal is going to be, let's figure out what number goes there. So I'm just going to call it k for now. Our goal is to figure out what k has to be. So let's get this on a new slide. We're going to move this over onto a new slide and examine this and see if we can't figure out what value of k lets us change our base from 2 to 10. And so what we'll do is we'll say, well, these two things are supposed to be equal. So 2 to the t and 10 to the kt are equal to each other. I don't know what they're equal to. I'm going to introduce a new variable, just a dummy placeholder variable that we're only going to use to make our life a little more convenient. Don't worry about what this is. We're calling it y. All right, well, this part right over here says y equals 10 to the kt. That's an exponential that we could rewrite as a logarithm. That logarithm would be the log base 10, because 10 is underneath our exponent, of y is equal to kt. But what is y? y, not only is it 10 to the kt, it's also 2 to the t. Because remember, we said both of these things were equal to y. They're equal to each other. So this y here is 2 to the t, which means I can replace this y with 2 to the t power. The log of 2 to the t is equal to k times t. Hey, we have a rule about this. If you're taking the logarithm of a number to a power, that exponent can come out front as a coefficient. T times the log base 10 of 2 is equal to k times t. There's a t on both sides of this. Let's cancel it out. Let's divide both sides by t. And we've found out what k is. K has to be the log base 10 of 2. And so what we find out is 2 to the t, that's the same as 10 to the log base 10 of 2 times t. We could go through this exact same series of steps here to find out that if we had something like 3 to the x and we wanted to make that 7 to the something times x, that something right here, that something would be the log base 7 of 3. If we took the log base 7 of 3 times x and made that the exponent on a 7, it would be the same as taking 3 to the x. In effect, what's happening is the 7 and that log base 7 are canceling out and leaving us with a 3. This 10 and this log base 10 are canceling out, and we're leaving us with the 2 to the t, 3 to the x. If I've got 1.49 to the x power equals e to the something times x power, that something in front of the x up in the exponent should be a natural log, log base e, of 1.49. This e to the and this natural log cancel each other out and leave us with a 1.49 that we raise to the x power. We can always change bases in an exponential function. Then we really ought to be able to do it in a logarithmic function, because we know that these things really are the same thing, just written in different ways. They're just inverses of each other. If I've got the log base 2 of x, and what I really want to do is see the log base 10 of x, what do I need to change? These things aren't going to be equal as they are. What do I need to change about this to make it be the same as that? That's going to be our next hurdle to jump over, is to find out if we can do it for exponential functions, how do we do it for logarithmic functions? What do we need to change on this to make it be the same as this? Make it be the same as log base 2 of x.